Welcome to Nuclear Chemistry, Unit 14. Section 14.1 covers transmutations. Our primary objectives are to describe what nuclear chemistry is and how it differs from traditional chemistry, define transmutation and describe the differences between natural and artificial transmutation, differentiate between fission and fusion, and finally to write nuclear equations for fission and fusion reactions. So what is nuclear chemistry? Well, pure chemistry can be defined as the study of the composition of matter and the changes that it undergoes. Nuclear chemistry, more specifically, deals with the changes in the nuclei or the charged cores of atoms. Remembering that the nuclei are made up of protons and neutrons, the charge on the nuclei is always positive. Nuclear versus traditional chemistry. Nuclear reactions, which account for radioactivity, differ from traditional chemical reactions in a variety of important ways. In traditional chemical reactions, elements and compounds gain stability by sharing and transferring electrons. However, in nuclear chemistry, the nuclei gain or lose subatomic particles, including, but not limited to, protons, neutrons, and positrons. Traditional chemical reactions are affected by changes in temperature, pressure, and catalysts, etc. However, nuclear reactions are not. Also, in traditional chemical reactions, though some reactions can create explosions and engulf themselves in flames, overall, the energy produced by a traditional chemical reaction is very small compared to the amount of energy produced from a nuclear reaction. Nuclear reactions are extremely large, as can be seen when looking at a star or what an atom bomb can do. So talking about transmutation. Transmutation occurs when the nucleus of one element is transformed into the nucleus of a different element. One element becomes a different element. And previous to this point we said that's not possible, but it truly is only under nuclear chemistry. And transmutation can occur in a variety of ways. The two forms of transmutation that we look at are natural transmutation and artificial transmutation. Natural transmutations involve a single nucleus undergoing a change. It often occurs because the number of protons, which we recall are positively charged, compared to the number of neutrons, neutrally charged particles, in an atom of the nucleus creates instability. The nucleus then decays on its own in a series of steps which eventually produce a stable nucleus, emitting radiation in the process. The matter has to be changed into something and often is changed into forms of energy. There are several types of natural transmutation, including alpha, beta, and positron decay. But the whole point of any type of transmutation from natural terms is simply to make the atom more stable at the nucleus. Artificial transmutation is often performed by a scientist in labs, where they change or manipulate the nucleus artificially. It's not doing it on its own, it's artificial, we are doing it to the nucleus. This occurs when a nucleus is bombarded with high energy particles with the intent of bringing about a change. A particle accelerator is used, and particles and subatomic particles are shot right at the nucleus of an atom. Unlike natural transmutation, this form of transmutation often involves several nuclei instead of a single one. One type of artificial transmutation involves a collision of a charged particle with a nucleus. Often the charged particle is a proton or an electron or something similar. Another type of artificial transmutation involves a collision of a neutron with a nucleus. The only difference being is a neutron is electrically neutral. Both types of artificial transmutation result in the creation of radioactive nuclei. So instead of the nucleus changing to become more stable, we're actually creating an unstable nucleus. Artificial versus natural transmutations. It's important to be able to tell the difference between the two types simply by looking at the nuclear equation from the reaction. A nuclear equation is very similar to a chemical equation in the way that it's set up, in the fact that mass must always be conserved. However, it differs in the nuclear equation because in a nuclear equation we look at atoms and subatomic particles in the splitting or fusing of atoms, whereas in a chemical equation we look to atoms and compounds creating or breaking bonds. Now we're focusing in here specifically on what's happening with the nucleus of an atom and what subatomic particles are created or given off. At a quick glance, to tell the difference between natural and artificial transmutation, one should easily look at the reactants. If there's a single element in the reactants, it's naturally occurring. This is also called spontaneous. Spontaneous just means it happens on its own. And we said that natural transmutations always start with a single nucleus and it breaks down to make it more stable. So shown here, there's a calcium atom. You can see the mass at the top and the charge, and it's breaking down, it's losing a positron, or a positive elementary particle, and giving off, in the process, it becomes a potassium nucleus. And then if there's more than one element or particle in the reactants, then we know it's being artificially manipulated. So here we can see plutonium is being bombarded with neutrons. So it's not choosing to break down, it's being hit by neutrons, which breaks it down into americium and gives off an electron in the process. And if you notice, the total masses on both sides of each nuclear equation shown here are equal. In the first equation you can see calcium is 37, and that's the only mass on that side. And on the other side, potassium's 37 plus 0 for the electron, and that keeps 37 at the top. Same thing at the bottom, the charges are balanced. On calcium you can see equals 20. And then on the other side you can see potassium is 19 plus the 1 plus from the positron, and that gives you a total of 20 on the other side. The two major types of transmutation are nuclear fission and nuclear fusion, and you do need to know the difference between the two. Nuclear fission is the splitting of a large heavy nuclei into smaller nuclei. A fissure, so to speak, is created within the nucleus and it splits. Nuclear fusion, however, is the combining, the fusing together of small light nuclei to create larger, heavier nucleus. In both reactions, the mass of the product is less than the mass of the reactants. However, it is not lost, it's simply due to the conversion of that mass to energy, as expressed by Einstein in his equation E equals mc squared. So in this example, you can see a picture of fission and fusion. You see a very large nucleus in fission splitting apart into two smaller nuclei, whereas in fusion you're starting with two smaller nuclei and you're slamming them together and fusing them into one nucleus. A nuclear fission reaction occurs when the atom of a heavy radioactive, which is already unstable, element captures a neutron. This creates extreme instability and the atom splits immediately. So it's already unstable and a neutron comes into play, making it so unstable that it breaks. The products of such a reaction are two mid-sized atoms and a massive quantity of energy released to compensate for the loss of mass. So the atoms aren't super small that it's broken down into, but they're much smaller than the original. The energy is produced because the laws of physics state that matter cannot be created nor destroyed, it can only change in form. The products of a fission reaction are highly radioactive, unlike those of a fusion reaction. Here's an example of fission. You can see a uranium atom here. The nucleus is very, very large, and a neutron comes in and hits it, and it creates an incredibly unstable uranium nucleus, and that nucleus snaps apart, creating a krypton nucleus in this case, and a barium nucleus, and 3 neutrons. And those neutrons can actually go out, and if there's other uranium atoms around, they can cause the same reaction and create what's called a chain reaction in this fission process. Fusion, on the other hand, reactions can best be observed by looking at the sun or any given star. Within our sun, atoms of hydrogen react with each other, and they fuse to build themselves into atoms of helium. Incredibly large amounts of energy are produced as a byproduct of this reaction, more energy than in a fission reaction. The massive quantity of energy is essentially what fuels our star. Unfortunately, we currently lack the methods of containing extremely high temperatures and pressures needed in order to complete this reaction. However, just recently we have been able to, for small amounts of time, be able to capture fusion and allow us to drain the energy from it. Here we can see 2 sets of hydrogen at the top. And remember, hydrogen is just a proton with an electron surrounding it, but we're only interested in the nucleus. And we can see that these hydrogen fuse together, and in the process they actually make hydrogen 2, which is a proton and a neutron. And then they find another hydrogen, and they fuse once more to create an actual helium nucleus. And those helium nuclei can fuse together, give off hydrogen, and create a more stable helium nucleus, which we see at the bottom. And those hydrogen can actually go back and take part in the reaction again. And so for the regions connection, we need to look at different types of questions. More specifically, which balanced equation represents nuclear fusion? And if we look through here, they give us a bunch of nuclear reactions, and so we can't cut out any by that. But we're looking specifically for fusion. Fusion means we're going to have one main atom in the products, but we're going to have more than one atom in the reactants. So if we look down through here, number 1 and 2 both start with a single element or atom in the reactant section, so we know there's nothing for it to fuse with. And we look down for 3 and 4, well, number 3 has 2 hydrogen coming together to make a helium, which sounds like a strong possibility. But looking at number 4 quickly, we see we have a uranium, which is a very, very large element, combining with a neutron, which isn't actually another atom or element. And so we are going to go with number 3 here, nuclear fusion, 2 small atoms coming together to create one singular atom. Another example, what kind of reaction is demonstrated by the image at the right? Well, if we look from top to bottom, we can see that a neutron is coming in and hitting a uranium atom. Again, it's a very small, or a very large atom, excuse me. And then you see from that the uranium starts to split and finally separates into a strontium and a xenon atom and a couple of neutrons left over. But the key here is we see a large atom splitting into 2 smaller atoms, meaning that this must be nuclear fission